good evening to everyone. Good afternoon to those of you who are about to have lunch, so on and so forth. Yes, as Andre said, I was volunteered to give a presentation, and hopefully it will be entertaining for all involved. Thanks for the opportunity. I'm still relatively new to UBC myself, so it's been pretty fun for me to listen to some of my colleagues. It's impressive work that's been presented so far. I'm going to talk about my research group's effort as just sort of a general outreach from UBC to Huawei. My research group is called the Programming Languages for Artificial Intelligence group, and we roughly work on deep probabilistic programming and affiliated technologies. I'm a CIFAR AI chair and the chief scientist of a spin-out called Inverted AI, which will come up later in the talk. So I sort of feel like I'm a bit of an evangelist for probabilistic programming, or need to, or explain it, because not many people know what it is, and I doubt that's any different in this particular crowd. So let me start by just saying what probabilistic programming is before we even get into what deep probabilistic programming is. Probabilistic programming is an emerging or emerged field at the intersection of machine learning, statistics, AI, and programming languages. And let me give you a rough sense. So many of us are caught up in the deep learning revolution, and that's all fair because of what it can do for us and society. And I would characterize deep learning as being sort of the computer science way of doing things. You have some input, a picture, you run it through some partially specified program whose weights you adapt via some sort of learning or optimization procedure, and then fix at inference time. And you run this whole stack forward to produce some sort of output, cat or not. This is what the entire endeavor of hardware, electrical engineering, computer science, so on and so forth has been about for quite a long time now. There is an adjacent field known as statistics that looks at the world in a very different way. Namely, they look at the world of data out there and they try to make sense of it. And generally, they try to make sense of it by imposing some sort of a model. And I'll have very little notation in this talk. All the notation I will have are y and x, and I'll explain them in just a little bit. But y are going to be observed, x are going to be latents, and a model is going to be a joint distribution of data or observables y. Okay, so we have some observed data. It could be, it doesn't matter. We'll give lots of examples later. We impose a model, and we'd like to ask questions about the world that involve the latent variables that you can't directly observe. Okay, Sid's, you can frame many of the problems that Sid was just talking about as inference problems. Where are the cameras? What pixels should be filled in? So on and so forth. So these are nice to build on. And statistics uses the tools of Bayesian inference, and this has not been mentioned many times during today's workshop because I think a lot of people think that it's impractical or complicated or whatever. But it's out there, it's understood, and the field of statistics has a lot to offer in terms of algorithms for solving what I refer to as inverse problems or Bayesian inference problems, where you go from an observed quantity y to some unknown posterior latent quantity x given y. So probabilistic programming is roughly about using the tools of computer science, so simulations, computational processes, language descriptions of problems, to do statistics. So we're going to look at the outputs of programs and try to figure out what inputs gave rise to those outputs using the tools of inference. Now, I'm assuming, again, I think it's a reasonable assumption that most of you know about deep learning and understand that deep learning arises because of the confluence of a large amount of data, automatic differentiation tools, really fast computers, right? So the most direct way that I can explain what probabilistic programming is to people with that background is to say that the gradient operator, backwards or grad or whatever, the gradient operator of languages that support automatic differentiation is to deep learning as the conditioning operator of languages that support automated inference is to probabilistic programming. So in other words, what gave rise to deep learning are languages that support automatic differentiation through operators that compute gradients. Probabilistic programming automates inference via providing languages that have conditioning operators. Okay? And languages for deep learning allow specifying and automatically solving forward function approximation problems via optimization, right? So, learn the parameters of a neural network, and then once you have the neural network, inference is easy. It's just a pass through this computation graph. Probabilistic programming languages allow specifying and automatically solving inverse problems via inference. Okay? It's a whole different ball of wax. So I've been involved in probabilistic programming for quite a long time now, and am one of the people who's led the charge in machine learning. And there's been a huge explosion in the tools, techniques, and capabilities of probabilistic programming languages over the last decade, really. I gave a NeurIPS tutorial in 2015 on this, and am trying desperately to finish a book called An Introduction to Probabilistic Programming, which is linked at the bottom. And over the last decade, we've moved from sort of one-shot statistics problems with fully specified models, that was what probabilistic programming was known for, through amortized inference, in other words, rapid inference in fully specified models, and now what the title of the talk is deep probabilistic programming, where we're doing this automated inference thing, where we need really, really fast inference, but we also need to learn the models. And this is where deep learning and probabilistic programming really, really collide in this bottom half. And most of the talk that I'll talk about, most of the things that I'll talk about today are in this bottom half. And I don't know how many of you have attended conferences or talks with Jan LeCun, my friend Jan, a decade ago or however long. He would give these talks where he would evangelize for convolutional neural networks by basically taking a camera and swinging around and showing how he could do dense scene segmentation, and that was super cool. And I didn't really realize how compelling it was when I listened to those talks, but obviously other people did. You're smarter than me, and picked up on this. But I sort of feel like deep probabilistic programming in particular is getting to this point where my principal job is to evangelize what we can do. It's not quite maybe as direct and as compelling as what Jan is showing, but if you put your thinking cap on, I think maybe some of these things will be relatively compelling. And unfortunately, Keynote takes over all my displays, so I can't see the chat channel. Andre, let me know if there are questions. Please interrupt me. I think I have a little extra time due to the schedule, although I won't try to consume it because I know all of us want to get going. But I'm going to talk about a bunch of case studies that have come out of my lab, and hopefully some of them will attract your attention. I was going to ask which ones people would like me to go through, but I'll just go through them quickly. And if you don't like them or you want me to spend a little bit more time on one or another, I will. We're going to talk about case studies in high energy physics, in composites manufacturing, in sort of really deep computational neuroscience, in high throughput gradient computations on parallel architectures, autonomous driving, and image and painting for various applications. And again, the point is to say what we can do with probabilistic programming now, just to try to get you interested in the field and to recognize that maybe actually there is something out there beyond deep learning. And I've put model on all of these slides to emphasize the fact that I use the word model correctly, which is to say that a model is a forward model of some phenomena. And an inference network is what various people have referred to correctly as a network that performs inference in this model to uncover latents given observes. So when I say model, I mean joint distribution and a generative model, more or less. So a case study. So the first case study is in high energy physics, where the model is a very large C++ simulation software package called Sherpa that simulates the standard model, and Géant, which simulates the Large Hadron Collider, the Atlas detector on the Large Hadron Collider, amongst other detectors. So what you see here is the model, and the significance of this particular example application is that this is about, I sat in my office in Oxford before I came here in about 2015 and said, what is the hairiest possible application we can put together to show what deep probabilistic programming can do? We said, okay, the fundamental particle interactions in the standard model are recursive. It's an infinite dimensional model. The software architecture, the model complexity is completely ridiculous. The real-time requirements are out of control, so on and so forth. So the model is what happens when high-energy particles come together and create their particle showers. The visualization of P of X here on the left It's not the particle shower, but that instead the control flow graph of the recursive procedure that generates events in at LHC energy levels. Okay. On the right, you see the output, Y, the observations that we get. And the challenge is to do inference in this model rapidly, repeatedly, given Ys, and uncovering what events actually took place, i.e., what particle masses, what momenta, what types, what interactions took place, so on and so forth. Basically, a posterior distribution over Feynman diagrams or something like that. It took a little while to get this published. It took a very long time for people to even understand what was going on, but this was a best paper finalist at SC19. It was a Gordon Bell Prize nominee, paper at NeurIPS, and currently still holds the record for the largest PyTorch, CPU-based PyTorch neural network training and inference. We trained on 32,000 CPUs at NERSC for about a month in order to get this to go. The high energy physics community is very, very interested in this. The point is that this is all possible because of an underlying probabilistic programming language at Canada Laboratory that we can wire directly into this simulator without ever touching the simulator. I know nothing about particle physics. I do know how to control simulators and generative models using the tools and techniques of probabilistic programming. And as a case in point, I'm going to show you another application that it uses exactly the same piece of software and the very similar, slightly more advanced tools and techniques in composite parts manufacturing. So we work with a company that works with Boeing, and those of you who can understand what's going on in this figure, this is destructive wing testing on a 787 airliner. Why 787? The 787 introduced composite wings, okay? So whether or not these wings break under load has a lot to do with baking muffins. And I know we have many different food cultures related here, but I think it's relatively apparent that when you bake a muffin, you want to make sure that it stays in the oven and achieves a particular temperature so that the center of the muffin isn't squishy or over dry or so on and so forth. You want the consistency and texture of the muffin to be just right. And that has a lot to do with how you bake it. And that's true of composite parts as well. They're effectively baked in an oven and the composite cures in a particular way. And it's very, very important that composite that you understand how that composite cured lest there be problems. So here we see in red a part of a wing sitting on a stand that would go in an oven. The yellow box here is a 2D cross-section through this part. The blue line here is a 1D cross-section through the part which starts right there. Convergent is our partner in this research. They build a stochastic differential equation-based, I don't know how it works, simulator that simulates the composite cure process through parts at all depths over time. And this is a slice of that part, a 1D slice of this part over, and this is depth in the vertical axis and time on the horizontal axis. And what you see in the video, excuse me for advancing too soon, what you see in the video is the prior distribution over temperatures that would be achieved in the simulator. Okay, so this is the model. The model is all temperatures, all times, all depths, and uncertainty arising from aleatoric, epistemic, so on and so forth sources. The inference problem here is that you cannot actually destructively test the part. You can't go in and actually measure in the middle of the wing lest you destroy the wing. So all you can do is look on the outside. You can put a thermocouple on the stand and you can measure the oven temperature over time. So conditioned on that, we use our probabilistic programming systems, the exact same one that we used for the standard model, to infer the maximum and minimum temperatures here in the middle of the part at a particularly critical time to ensure that the parts achieve a uniform, consistent, well-baked muffin kind of state. And it turns out that using general purpose techniques, we can also build surrogates for this model that go 90 times as fast, so that inference is 20 times as fast, such that it can actually be used in real-time part production pipelines. This same software called PyProb, which it also has an associated interface that allows us to interface to various simulators called PPX, is publicly available. It's open source, so on and so forth. We also did some late-breaking COVID research, which won an award from CIFAR last year, where we used PyProb in conjunction with the Fred epidemiological simulator to do policy planning framed as posterior inference, trying to achieve a particular goal. Cool, fast and furious. All right, so this is deep probabilistic programming where you have a pre-specified model and you want to do inference really fast. I'm saying that there exists probabilistic programming systems that allow you to do this with arbitrary simulators. This is some of the work that comes out of our group. Now for something even more crazy, where we start to advance towards model learning and more advanced probabilistic programming systems, including, for instance, Pyro, if you've heard of that, or Edward, so on and so forth. We contribute quite a lot to Pyro. So the sort of crazy computational neuroscience thing that we're doing in deep probabilistic programming involves the C Elegans Roundworm. This is good fun. C elegans is particularly cool because it's the only organism for which the entire connectome is known. In other words, all the wild type neural circuitry is completely identified and stereotypical. We know exactly how many neurons there are, and we know exactly how they're connected to one another. And there exist, again, partially specified software simulators, and this is where this deviates slightly from the previous ones, where the science is good enough that we know the values in the simulator more or less. We know the model. Here we don't know all of the models, so we're going to learn part of the model while we're doing inference in this. The fun part is that neuroscientists are crazy and have developed techniques to actually resolve and view the activity of 25% of the C elegans neurons while it's behaving. So what you see in the upper right-hand corner here are calcium fluorescent images of the cell activities of like 25% of the neurons in a C elegans worm as it is behaving. Now, coupling a probabilistic programming system with the existing simulators, we can take just what we observe. The only Y that we have are the observed neural outputs of these 25% of the cells of C elegans, and recover things like all of the rest of the neural states, and perhaps more amazingly, the body shape, and I apologize for the non-smooth video display here, the body shape of the worm, literally reading its mind. I assume that's not a question, doesn't sound like one. Okay, so again, here we had to learn part of the model, but the point is that a very similar probabilistic programming system is used to condition on the observed calcium fluorescent images and infer the latent body state and additional mind state required to reconstruct the relative trajectories. Okay. Moving on, now we're in Pyro land for sure, where we're doing model learning and simultaneous amortized rapid inference using the tools of deep probabilistic programming. Here we're going to look at predicting the performance, and this is something that's very close to Lily Wang's proposed work for Huawei. Here we're going to look at learning a model of a high-performance computing cluster so as to improve the throughput of stochastic gradient descent updates. Okay, again, for those of you who are listening and thinking, my God, how could you possibly be doing these sorts of things? Again, probabilistic programming is sort of like, the tool chain that we're building is kind of like just building a programming language. And unfortunately, we're still at the very beginning where we have to show people what we can do so that we can convince them to use our programming languages, which is a little bit crazy. But so case study, you have a big parallel computer and you want stochastic gradient descent to go really, 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 really fast. What you don't want to do is wait around for stragglers. Now, what the heck does this have to do with flies? Well, we use literally the same code for three things. and the same probabilistic programming system, so on and so forth. So here are two flies in a petri dish. This is a multi-agent system. These flies have some internal state. They have some history of behaviors, and we might want to project where they're going to go and how they're going to interact in the future. Okay, so what we see here on the left is a multi-agent system, basically a semi-supervised deep variational RNN, programmed in a deep probabilistic programming system, conditioned on various things, including the historical position of flies, not shown here. Here's a fly on the left, here's a fly on the right, and what we can do is predict with uncertainty where the fly will be in the future. Okay, that seems feasible. What does this have to do with doing the kind of PyTorch deep neural network training that I talked about when we were doing the standard model thing? Well, we trained on Cori, which was the fifth fastest machine in the world at the time we did the research. And here's an example of the kind of thing we did. We needed to learn how to do stochastic gradient descent very quickly to learn our amortized inference artifacts in our deep probabilistic programming system, PyProb. Okay? So there we did 32,000 CPUs, but here's a 2,000-way job running stochastic gradient descent. And for those of you who know stochastic gradient descent, it's fairly clear that you don't really care if you get all of the gradient computations done. In fact, you may be able to do a better job training your neural network if you throw away some of the computations. Again, this is very similar to what Lili has proposed to do. We've just done something similar before. What you can do is you can train a model to anticipate how the cluster will behave, where the contended nodes will be, how contended nodes in one rack affect contended nodes in another rack, so on and so forth. So what we did is we learned a deep nonlinear dynamical systems model of a 2,000 worker array here on Cori. Think of it as 2,000 flies interacting, right? And then using a teeny bit of very simple theory, we said basically you just don't have to just forget all of the workers that are beyond some cutoff. And the cutoff here is shown in red. Run stochastic gradient descent mini-batch computation runtimes are on the vertical axis, number of workers are on the horizontal axis. And if you throw all the laggard workers away, which will be different depending on your model predictions and the conditioning that you do on how the workers, the continual conditioning that you do on how all the workers perform, you can achieve very, very significant stochastic gradient descent iteration speedups and overall training performance improvements. Okay, cool. So what else can you do? Same probabilistic programming system, same model in this particular case, although we're starting to change the model ever so slightly. There are significant applications in, for instance, autonomous driving. And one of the things that I'm doing is participating in a spin out from UBC, which is also participating in the multi-agent prediction problem called the Interpret Challenge, or the Interaction Dataset-Based Prediction Challenge, which was run this year at NeurIPS. We didn't win it, but we did pretty well. We can predict the trajectory of congested scenes like this of all the agents in the scene to 40 centimeter accuracy, which is pretty much close enough to be okay, 3 seconds in advance. So what do? We apply the same kind of multi-agent model that we used in a deep probabilistic programming system to learn the model and then to perform rapid amortized inference in the model. Here, conditioning on the gray historical trajectories. Let me choose one here. Gray historical trajectories and predicting the green predictions. The nice thing about the probabilistic approach is that you get uncertainty and sample diversity in the characteristic predictions. Again, we're looking at 1 second of history. That's what we're conditioning on, and predicting 3 seconds into the future. I think there were some control people on. Once you have a model with this kind of fidelity, you can embed it, also framing, I don't know why the video is not playing here, also framing reinforcement learning as inference, which is something that Sergey Levine and my group have been doing for quite a long time, and use these same models in model predictive control for actual control of vehicles, although that's not the specific focus of inverted AI. The the predictive models are instead. And in a way that would require reading the book and taking the course, I'll say that the very last thing here is that the emerging field of meta-learning and neural processes and these sorts of things, they are exactly the same as amortized deep probabilistic programming inference. They are literally exactly the same thing. And we've been doing a bunch of work at the interface of statistics theory, trying to understand how uncertainty is propagated in deep neural networks and so on and so forth. In particular, looking at a variety of applications where we do conditional generation, where the amount of condition is extremely small. And this has knock-on applications in low power classification, regression, deep learning systems where you do attention-based processing of images. Here, what you see is a learned deep probabilistic program that learns to conditionally generate from an arbitrary, here, a different number of observations. So the context is 1 pixel, 2 pixels, 3 pixels, 5 pixels, 10 pixels, 15 pixels, 30 pixels, so on and so forth. It learns to produce a posterior and then a posterior predictive, which is which are these sampled images, that is properly calibrated in an uncertainty sense, particularly in the low sample complexity regime. And this ties to deep probabilistic programming in a very technical way, but I'll just leave it at meta learning. The whole field is exactly equivalent to amortized deep probabilistic programming inference. And we've been doing this for quite a long time. So we've got a lot to say about it. Anyway, so that's what we're up to in the programming languages for artificial intelligence group. The general aim of my group is to build tools that advance us towards AGI, which is, of course, the the big goal, the grand banana, as it were, and to produce technologies that are commercially viable. I'm particularly interested in enhancing the entrepreneurship impact and effort at UBC, which is growing in sophistication rather rapidly. And I hope through this talk that at least this slide makes sense now, in that we all know deep learning and languages for deep learning allow specifying and automatically solving forward function approximation problems via optimization. What I've talked about the entire time are applications of probabilistic programming, places where we use probabilistic programming languages to specify interesting inverse problems. And again, just to recap, we had the high energy physics problem, we had the computational cluster prediction problem, we had the prediction of where the agents are going to go in a driving setting, we had, predict the posterior predictive in-painting or infilling of images given a particular context set of observed pixels. These are all framed as inference problems, framed as inverse problems, and solved via automatic amortized probabilistic programming inference, deep probabilistic programming inference. So thank you very much for your time. That's it. And I'm very, very happy to take questions.